Yes, in the following two lectures, we will discuss black hole perturbation theory. I think in the past lectures, we have discussed the problem of binary inspiral, right? So when these two compact objects are far from each other, then you basically use the quadruple formula to compute the gravitational wave radiation. And when these two objects get closer, then this Newtonian approximation gradually breaks down. In that case, you need to use the so-called post-Newtonian formalism to describe the system. All right, so basically, this post-Newtonian formalism is Newtonian theory plus corrections in the expansion of 1 over c to some power. Yeah.
Could you switch on the blackboard light?
The light switch off.
No, switch. Close on.
It should be alright.
Perfect.
Okay, so basically this post-Newtonian theory is very successful in describing the inspiral part of a compact binary mergers. But there are cases where this theory completely fails. So there are two famous scenarios. One scenario is that when this Pn fails. So one scenario would be after these two black holes merge, and then they settles down to a final black hole plus some perturbation in the space-time. So it's almost a curved rotating black hole, but then there is some perturbations. So in this case, this is a binary black hole bring down. You cannot use post-Newtonian to describe this system. So in the other case, you have a supermassive black hole. And you have a stellar mass black hole orbiting around this supermassive black hole. In this case, it's usually called extreme mass ratio inspirals. So this happens in the galaxy centers, where you usually find the supermassive black hole. Okay, so basically this is, let's say, this is already already detect this. And Lisa will see this. So in both cases, the reason why post-Newtonian theory fails is that either we're looking at the region of space-time where gravity is very strong, okay? So the gravity is strong. And if there is a test particle in this space-time, the speed is comparable to c. remember the post-Newtonian expansion is an expansion to 1 over c. So when the speed is very close to c, then it fails.
How close to C can that stellar mass black hole get?
So it can be a great fraction of c, right? So depending on this distance. So when it's very close to horizon, it can be very close to c. I guess you in your GR course you must have learned how to compute the geodesic motion in a curved spacetime, right? So you can figure out by yourself. Okay, so if PN theory fails, how do we deal with this system? So that's well, we. Okay, so let me see how this. Okay. So when PM fails, then we need to use some other techniques to describe this system. That's the black hole perturbation theory. So in black hole perturbation theory, instead of trying to like perturb around a flat spacetime or Newtonian theory, we perturbed around a known solution, which is the in many cases is the Kerr solution. Okay. But if you are dealing with more exotic black holes, you can perturb around those exact solutions. But this is the most astrophysically relevant one. Okay. So basically, in black hole perturbation theory, we decompose the metric perturbation into a background solution plus perturbations. Okay, the background solution is known, and then we solve the Einstein equation in the expansion of epsilon. So we assume the perturbation is small. Of course, the leading order, so let's assume that the source, for now let's assume that the source is 0. So the leading order equation is, of course, G mu G background equals 0. Okay, this is the zeroth order. Zeroth order equation, okay? And the first order equation will be something like gradient square HAB plus okay. There are 3 more terms. Okay, so here the gradient and the r's are all respect to the background metric. Okay, and also the Ricci tensor, the Riemann tensor, Ricci tensor here. The H is basically HAB, GAB background. Okay. So we have discussed, I think in the past lectures we have discussed linearized gravity, right? So for linearized gravity, then you can just correspondingly just use the flat metric for the background, and then this equation will simplify. Okay. But this is in general, so you can plug in any metric in the background. In black hole perturbation theory, of course, you would like to plug in the Kerr solution. Okay, so this is a general equation for metric perturbations. But let me, before I move to a more specific discussion on the perturbation of Schwarzschild and Kerr, let me draw a diagram here just to illustrate the region of applicability for binary systems. So this is the mass ratio. Okay. And this is the separation. For compact binaries. So when the separation is big, the post-Newtonian theory should apply. When the mass ratio is big, then the space-time is basically the big black hole space-time plus perturbations. Then this black hole perturbation theory would apply. Okay. In principle, the numerical relativity applies for the whole regime, but for practical reasons, in these regions, the computational cost will be too high. So people usually just use numerical relativity to compute small separation and close to one mass ratio cases. Okay. Any questions so far? Okay, so now let's discuss the perturbation of Schwarzschild black holes. So why do we start with Schwarzschild black holes? It's because this black hole is very simple. It has maximum symmetry, right? It has the rotation symmetry. And we know that if the background has this symmetry, we can usually use it. For example, if you want to describe a scalar field in a space-time with spherical symmetry, any scalar field. Right, so you can usually just spherically decompose this scalar field.
So you're also taking the scalar field to be spherically symmetric in this case? Even
the background is Spherical symmetric, but the scalar field is not.
It's not. Oh, okay. Oh, that's really good. Okay.
So you could decompose the scalar field in spherical harmonics. I mean, if the background does not have spherical symmetry, you can still do this decomposition. It is just only if you have spherical symmetry, then different spherical components will not talk to each other. Okay. So the equation governing these different modes are completely separable. Okay. This is for scalar field. If for vector field, this is scalar. And for vector field, we can similarly define vector spherical harmonics. So let me define 3 different types of vector spherical harmonics. So we call it Y1. So this will be the radial univector times YLM. And Y2. This is R gradient YLM. So in the component basis, this is E theta, pi theta, Y Lm plus E phi, pi phi, Y Lm. The third basis, Y3. This is R cross gradient YLM. Okay, so these 2 vectors are usually called polar vectors, and this is usually called the axial vector because they will have different properties under the parity transformation. Okay. So, for example, if you have if you consider a 3-dimensional space and you have electric field. For example, if you have an electric field, you can always decompose your electric field to be ER component. Y1 plus So this is similar to the scalar case. You can always decompose your vector in these vector spherical harmonics. So this also, okay. So it's often useful to distinguish this one from the rest too, okay? Because this y1, which is the radial vector times y, so it does not live on the unit 2 sphere, while the other two vector harmonics lives on the unit 2 sphere. So let me use some other notation. So let me define YA LM be partial A YLM, while this A, capital A, is theta or phi. Okay? For the vector harmonics live on the unit 2 sphere. And XA LM equal to epsilon AB, the Christoffel symbol, partial B YLM. So you can see that this one is basically your Y2, and this XA is the Y3. But this is already written in the covariant form. Okay. So this is a polar vector on the unit sphere. And this is the axial vector on the unit sphere. This epsilon AB is the Civitar tensor on S2. And let me remind you that on this unit sphere, the metric perturbation is just, the metric on the unit sphere is just sine square theta d phi plus d theta square. Okay, so with this covariant form, if we want to decompose a tensor, okay, in addition to scalar and vector, if we want to decompose a tensor field, a 3D symmetric tensor, so we can always decompose this tensor V to the component that's scalar on S2. Okay, so this is basically the VRR component, and some component are vectors on S2. So these will be the VR A component and the tensor component, the real tensor component on the unit sphere. This will be the VAB component. So let me explicitly write them down. So the scalar component on S2 is and vector component and the tensor component on S2 VAB. yeah, we have discussed the scalar basis, the vector basis, but we have not introduced the tensor basis, but we will do it here. So this is DLM omega AB YLM. Of course, this is a tensor plus ELM YAB LM plus FLM XAB LM. Okay, so these tensor harmonics YAB and XAB are defined as DA, DB, YLN plus LL plus 1 omega AB YLN. And XAB will be DA XB plus DB XA. Okay, so of course this is polar, and this is epsilon. And the D's are with respect to the metric on the unit to sphere. Okay. So now with the scalar, vector, and tensor basis, we can decompose all the scalar and vector and tensor fields. If we want to deal with four-dimensional tensor, it's very similar. So for example, for metric perturbations, by the way, you can look at the paper by Martel and Bassan. More details. This covariant formation of structural perturbations. Okay. So for metric perturbations, you can similarly decompose different components. Look at different components of a metric. For example, let me write it as the first set of metric perturbations is like P, PT, P, TR, and TRR. So these are scalars on the unit to sphere. One of the components is TR, and the other components belong to the unit to sphere. So this is P. So this is either PT theta, P phi, PR theta, PR. So these are vectors on the unit to sphere. And the third family lives on the unit to sphere. So this is the theta phi components. So with this decomposition, we can explicitly write down the formulas for these 3 different families. So basically, the scalar part has 3 components. The vector part can decompose using the vector harmonics. And tensor part. So we have 3 components here. Okay. So with this decomposition, then we can rewrite this perturbative Einstein equation. Okay. So the different harmonics mode will separate out because of the background symmetry, and then you basically get differential equations only on these metric quantities HAB, JA, HA, the K, G, and H2. Okay. Okay. So the Einstein equation, I will not write down the decomposition of Einstein tensor in terms of these tensor harmonics, but you can do it in a similar way. So at the end, then using this perturbative Einstein equation, you can get 2 types of master equations. For Schwarzschild perturbations. So the first type is associated with so let me associated with the harmonics. The polar Sometimes we call it the even parity harmonics. And the second type of master equation is associated with odd parity harmonics. So the even parity master equation looks very simple. So the principal part is basically partial t square plus f partial r minus a potential term function of r acting on a quantity which is a function of t and r equal to some source term. Okay. So here, this wave quantity phi even is basically a combination of the even parity part of the metric perturbations. That is k minus 2f kappa and this potential term okay, and here the f is just 1 minus 2m over r, and this kappa here is l minus 1 l plus 2 plus 6m over l. So by manipulating those even sector of metric perturbation, the perturbatory Einstein equations, then you can arrive at this master equation. Okay. Here the source term, of course, is 0 if it's a vacuum space-time. So for the other case we discussed, so in the black hole ring-down stage, this part is 0. But if you are studying the Emery problem, the system that Lisa will see, then this part is non-zero. Okay. So by deriving this equation, we have applied the so-called Ricci-Wheeler gauge. So in this gauge, the even parity quantity, the j's and the g are all set to 0. Okay? So that's why there is no j and g here. Okay. This is the even parity equation, and there is another equation for the odd parity. The odd parity equation looks similar. So it also has partial t square plus the radial derivative, but then this potential term is different. Odd potential is different. So in this case, psi odd is defined as 2r over L minus 1, L plus 2, partial r ht minus partial t hr minus 2 over r ht. And odd potential is L minus pi plus 1 times L r square. Okay, so this is a odd parity master equation. So usually this equation is called Ricci-Wheeler equation. Right? The other part is the really Moncrief equation. So in the Ricci-Wheeler case, we set H2 equals 0. So there is no H2 here. Otherwise, H2 will be here. Okay, so now the whole problem of solving the Schwarzschild perturbation becomes solving these two wave equations. So these are 1 plus 1 wave equations. If you want to, for convenience, usually one defines this so-called tortoise coordinate. So dr star equal to f minus 1 dr. So basically, one convenient choice is r star equal to r plus 2m log r minus 2m. So using this tortoise coordinate, then this part, for example, just becomes partial square partial r star. So, okay. And if we solve this wave equation in the frequency domain, for example, it's right. E to minus I omega t. that equation just becomes omega square plus d square dr star square minus v even. So this is in the sourceless case. Okay, so in the frequency domain, then we are just solving an ordinary second-order differential equation. So if we want to look at a wave in this case, so this will be T. This is R star. Then there is a potential term this for both even and odd parity. So this is your V odd or even. So I've not shown this, but you can verify by yourself. The peak of the potential is, for both V odd and V even is at R equal to 3m. Okay? So basically, the wave will be scattered by this potential in one-dimensional case. And usually, if you have away from the potential, then the waves, so away from the potential, on the left-hand side, for example, the waves will just prefer probably this way because this is the horizon. Right. So if there's no such term, then this V, then so this psi will be psi either a function of t plus r plus psi prime, function of t minus r star. But because this is a horizon, usually nothing comes out of the horizon, right? So then there is no such component. There's only one component. Similarly, here, at infinity, you can also have two components. So the V is also 0 at infinity, so you can have psi A, t plus r star, plus psi B, t minus r star. Okay, so one of them, this will be the ingoing piece of the wave, and this will be the outgoing piece of the wave. But so this is the generic boundary conditions. But for black hole perturbations, for example, if you want to look at the ring down of a Schwarzschild black hole, and the infinity usually you just get rid of the ingoing piece because you don't assume any driving gravitational wave to the system, so you can get rid of that. So there is only outgoing piece. You also impose outgoing boundary condition at infinity while imposing the ingoing boundary condition on the horizon. Okay. And similar to all the elastic systems, with this wave equation, you want to ask question that what will be the eigensolution of the wave equation? So if you look at a cavity, then it's easy to find out the eigenmode of the cavity, right? So light in the cavity can easily solve for the eigenmode. But if the cavity is open, in the sense that there is waves leaking out of the cavity, then if you want to solve for the eigenmode of the cavity again, then you will find out that eigenfrequency will be complex. So usually omega, the eigenfrequency of this system, will be a real part plus the imaginary part. The presence of the imaginary part is due to this open boundary condition. So the waves will go out, and any eigenmode will lose energy in time. So the time dependence of the amplitude. Well, this is the oscillatory part, but then there is a time-dependent decaying part because of the open boundary condition. Okay. So the similar thing will happen here. So we have an open system. So whenever we excite a wave in the domain, the wave will either go into the horizon or escape to infinity. So if we want to solve the eigenmode of the wave equation, we will also find complex eigenfrequencies, okay, in general. So intuitively, if we want to understand the eigenmode of this system, we can look at the WKB limit. So this is a limit that the L is much, much greater than 1. So when L is much, much greater than 1, so then the potential term will be very big, because you see this term will be very big, and similarly this term. Okay. So in this case, you will have a very big potential, and you want to look at the eigenmode in this case. So this peak is very high. And if you want to look at this problem, then the boundary condition is still outgoing at infinity and ingoing at the horizon. So if you want to have right-going waves here and left-going waves here, then basically this omega square in the wave equation has to be roughly equal to the V of the potential at its peak position in the WKB picture, right? So if omega is smaller than this potential, well, then it cannot penetrate through this potential well. If omega square is bigger than the peak of the potential, let's say if this is right going, then this part has to be right going because it has positive energy everywhere. So this part is right going, this part has to also be right going. This has to be right going. So this violates boundary condition. So that means the omega square has to be roughly just equal to the peak of the potential. So you can plug in, for example, the expression for the V's. The peak is at r equal to 3n. Okay. So this is, we will get omega r is roughly square root of L times L plus 1, 1d7n. So this is roughly L plus 1/2. This 1 over square root of 27m is basically the frequency of the light ring of Schwarzschild black hole. Okay. So this basically the WKB analysis tells us that the real part of the quasi-normal frequency is somehow seems to be connected with the light ring frequency of the same black hole. And this is not a coincidence. We will discuss this in the next class. Okay. Basically, if you also apply the WKB analysis, basically run this peak condition. Okay. So you basically solve the equation in this regime. You'll also find that okay, I have to erase something. You'll find that the imaginary part of the frequency omega I is basically square root of 2 times d square v dr star square at the peak divided by partial v partial omega at the peak. Okay, it's by WKB. So if we want to go beyond this WKB limit, if L is not very big, then the wave equation has to be solved numerically. And usually people use the so-called Lever's method, so I will not discuss it here. You can read the Lever paper. Okay, so it basically Lever decompose the wave equation in a set of basis functions, and then it solves for the coefficient of the basis functions. But it turns out that this WKB approximation is very good, even for the case that L equals 2, right? So the gravitational perturbation starts with L equals 2. The wave-like perturbation starts with L equals 2, but then it's still very good.
Sorry, is omega I positive all the time, or?
Yeah.
Okay. Yeah. So the derivative of the potential is negative?
Yeah.
Okay.
So if you look at the mode spectrum, so for different L's, it's like this. Okay, I think they do not lie on the real axis. So this is for different L. Let's say this L equals 2, L equals to 3, L equals 2, L equals 3. But then these different points are for different overtones, this n. Okay, so this is for n equals to 1, n equals 0. Okay. So the branch is like this. All right. I think that's it for today. So next time we will discuss the perturbation of rotating black holes.